I suspected that the reason for this rough periodicity was something to do with the sky. But I was searching for it and couldn't find anything. So essentially I gave up. I didn't have an explanation.
Jan Weiser, he reconstructed the temperature using a geochemical record. And the difference between that reconstruction and what I was using is that Jan Weiser actually reconstructed the actual temperature. So he knew exactly how warm it was and how cold it was. So I emailed him.
One evening, I was sitting in my office working. Suddenly, an email popped up, and this was near Sharif. And he says, well, I may have an explanation for you. He was telling me that he was working on cosmic rays variability over the more or less the same time intervals, and that the variability in the amount of cosmic rays hitting the Earth over this time interval was more or less similar to the variation in those oxygen atoms or in the climate which we observed.
After I teamed up with Jan Weiser, we had an actual temperature reconstruction. And what we could learn was that it was colder here on Earth by something like 5 to 10 degrees when we were inside spiral arms of the galaxy. Nobody found anything like that before, and we were simply amazed from it. But more interestingly, what it means is that cosmic rays are the main climate driver on Earth, at least on geological timescales. And the only explanation you have for it is Sven's Mark theory about the cloud cover. When you compare the geological record to the astronomical record, that's what you get. You see that the two barcodes give you the same product. The black line is the geological reconstruction of the temperature on Earth using the geochemical records of Jan Weiser. And what you see in the red is the cosmic wave flux variations. When both things are added together, they correlate very well. Statistically, it's very significant, but you don't have to believe the statistics. You can just look at it and realize that it's very meaningful.
It's been said so many times that the sun has not been responsible for the heating we have seen the last maybe 20, 40 years. However, if you look at the data, for instance, the ocean data, you will actually see that there's a very good agreement between temperatures and solar activity. And what you see is the temperature of the ocean down to about 50 meters. But if you compare the overall agreement with how the red curve is varying, it's very good. And the red curve, that is the cosmic rays. That is how the cosmic rays have been varying over this period. So we actually see, even today, that the sun is dominating the temperatures or how temperatures evolve. It has done so in the past, it's doing this now, and will also do it in the future.
An experiment like the one taking place here in Copenhagen is crucial because if successful, it will shed a lot of light on the physical origin of the link between cosmic rays and climate. And this will be the last piece in the puzzle which would make the picture complete.
So the effective aerosol background corresponds more or less precisely to what you have over the ocean. The experiment is not just something that you turn on and then you get the result. You get many, many results, and you do a lot of experiments, and you try to see if everything is consistent with that interpretation that you are giving.
The results of this experiment, hopefully we will know exactly how the sun affects climate, how it modulates the cosmic rays reaching the Earth, how cosmic rays control the amount of ionization, and how ionization controls climate, and through most probably formation of cloud cover.
It's very interesting after nearly 8 years of work that we finally got to this phase of trying to understand these experiments. All the bits and pieces was done over nearly a year. So it's not like from one day to another you sort of a sudden jumps up and says, fantastic, we got the result. It's not like that. It's actually hard work. Do you think? I mean, there's always a degree of uncertainty when you do experiments because you are constantly questioning everything you're doing, whether it's right and wrong. But we have been very, very careful, and we have done many tests on these ideas. So I think, I truly think that we have found a very, very important mechanism. And the mechanism was a big surprise how it actually worked. It's far-fetched. I mean, this is 0.34 ppb. Yeah. So it's very, very low. What we find when we mimic a higher flux of cosmic rays is that we actually produce more aerosols in the chamber. This actually means that cosmic rays are producing aerosols, and these are the aerosols which are responsible for forming clouds in the real atmosphere. Through our experiments, we have found a new form for atmospheric chemistry, which we think is responsible for the formation of new aerosols and therefore also for clouds in the Earth's atmosphere. And it shows that events in the universe are driving climate here on Earth to an extent that has never been understood before.
A large part of the clouds that we see in the sky is really a result of this process that we have investigated experimentally. But of course, now we have to see how other colleagues react to our findings, and that will be very interesting to see how this work will be received. But I think we have done a very good work, and I'm very pleased that how everybody has been working on this project. So this is a culmination of many years of work. This is really nice.
We thought we had a really scientific breakthrough in the understanding of how cosmic rays affect the Earth's cloud cover and therefore also the Earth's climate. But for very strange reasons, we could not get the paper published. I think we submitted it 4 times to different journals, and we still could not get these results published.
Henrik Svensmark and his group had very nice results, and I would have expected them to be published immediately, a few months after they found it. Instead, it took them 16 months to publish it, and the reason, I think, is because of reluctance of the climate community as a whole, in particular those who are supporting the anthropogenic greenhouse gas theory, to accept the idea that this new theory, which is already shown to be supported by a lot of empirical evidence, is also supported by experimental evidence.
The most frustrating part about the rejections was that there was no real critique that we had done anything wrong. It was things like, it's not interesting, it's too long. There was no real critique of the ideas, so therefore this type of rejection was even more frustrating.